Welcome back. And what we're doing is we're going to use some examples of concentration tables versus time in order to figure out the rates of reaction. Okay? So we've got this reaction that says 2 NO2s goes to 2 NOs plus O2. So we've got nitrogen dioxide turning into nitrogen monoxide and oxygen. And we've got data for the concentration of NO2 versus time, the concentration of NO versus time, and the concentration of O2 versus time. And you can't really look at this data and clearly see, is this linear, is this not linear, or anything like that. So we just kind of have to deal with it as we go. We could plot this data, and then you could probably see it pretty easily. In fact, we will do things like that, especially in our lab work. But for now, what is it asking? It's asking two questions that we're going to try to answer. One is, what is the initial rate of reaction? So we've got to define what that is, because I haven't used that term yet. And then what is the rate in the interval from 300 to 350 seconds? Because remember, when we're talking about rates, since a lot of reactions have rates that change over time, because it's faster when you have more of it, slower when you have less of it, we have to specify the time interval. Initial rate. What does initial rate mean? It means the rate when you first start the reaction. It technically means the actual rate at 0 seconds, the moment the reaction starts. But that's impossible to calculate. We can't calculate a rate from a single point because a rate is delta. It's a change. And so what we do for initial rates is we use a reasonable time period for figuring out how the reaction is changing. If we have a fairly slow-moving reaction, we might be able to use just the first 2 times, or we might be able to use the first 3 times. It depends on how much data we have. Here, we're not taking a whole lot of data. We're taking data at 0 seconds to 50 seconds, right? And my concentration changed, if you calculate it, by about 21%. That's a decent change, right? So it's not like we have really fine-grained data here. So to me, initial in this case might mean, hey, I'm just going to use the first 2 data points. What you'll find, especially in the lab, is we're going to have some data where from 0 to 100 seconds, a computer took the data and we have 5,000 points. I'm just making up numbers. Well, if we have 5,000 points, we don't really want to use just those first 2 data points. We might use the first 100 data points to get us an indication of the rate. And part of it is we'll plot it, right? If we have a rate that changes like that, it's huge, huge change, then yeah, we're going to be a little pickier about choosing that. If we have a rate that's kind of like that, okay, yeah, it's changing over time, it's sloping down a little bit, but maybe we can use a slightly wider range. So here's the fun part that comes into being a scientist. You have to decide what's appropriate for this initial rate. And someone next to you might decide something slightly different and get a slightly different answer than you. Are you both right? Well, you might be. If you have a reasonable justification for why you chose that, then you might both be right, even though you have different answers. It's fantastic. Science is not cut and dry, right? There's always some judgment involved. And as long as you're clear about the judgments you make and why you made them, that's good science, right? Because then somebody can reproduce your judgments and see, oh, do I get the same answer they do? Or they can say, well, I didn't like your judgment. Let me do my judgment. And then we can talk about the differences between our answers. And maybe we decide that one judgment is better than the other. That's the fun and interesting part of science. But I think for this time, we're going to go ahead and just use this 0 to 50 second data to find the initial rate of reaction. Now, we have got data for everything. So we have a plethora. We have a huge amount of data. We've got for NO2, NO, and O2. And remember, the rate is going to be defined as minus 1 over 2 times the concentration change of NO2 over time. Or you could write positive 1 over 2 times the concentration change of NO over time. Or you could even write the positive concentration 1 over 1. You don't have to write the 1 over 1 if you don't want to, but you can, times the change in concentration of O2 over time. I could calculate any of those, and I should get the same answer. In fact, we will calculate it using 2 different ones. Let's go ahead and calculate it for NO2 first, since that's the first one we have. And so we're going to say the rate is minus 1 over 2 times the change in concentration of NO2 versus time, always final minus initial. So I'm going to take my final concentration of NO2 is 0.0079. I'm going to subtract off my 0.0100 molar. Notice I just put the molar on the second number. That's okay. When we're subtracting off, sometimes we'll put molar just on, or units on just on one of the numbers in there to be clear what we're doing. It's best to put it on both of them, but you know, I get lazy too. And then what do we decide? Our time is 50 seconds minus 0 seconds. Oh, I forgot my negative out here. I've got to have that negative 1 over 2. If you calculate that, you get 0.0079 minus 0.01 is going to be minus 1 over 2 times 0.0021. And that's going to be a negative in there. I didn't leave myself much space. So it's going to be a negative 0.0021 molar divided by 50 seconds. You plug that into a calculator, and you get 2.1 times 10 to the minus 5th molar per second. Don't worry about the numbers too much, right? It's 10 to the minus 5th. Is that small? Is that big? We'll get there in a little while, but just make sure you're putting in the numbers right for now. So we get a rate of 2.1 times 10 to the minus 5th molar per second. Let's go ahead and figure it out for NO. So for NO, this was calculated using NO2. Let's go ahead and calculate it using NO. Let's use a different color. We'll use blue. Here for NO, rate's going to be the positive 1/2 times delta NO over delta T. So we get 1/2. We look back at our table. Our final concentration was 0.0021. Our initial concentration was none because we started with nothing. We don't have to start with nothing. We can start with something other than nothing. That's okay. But in this case, we started with nothing. 50 minus 0 seconds. And if you do the math, you get 2.1 times 10 to the minus 5th molar per second as your rate. And that's usually going to be our unit of rate. Molarity is by far the most common unit that we're going to use for concentration. Seconds is by far the most common unit we're going to see for time. We can write concentration, or we can write them as molar per hour, molar per day, right? For very slow reactions, maybe we'll do molar per hour, but it's most common to write molar per second. All right, we get the same number, 2.1 times 10 to the minus 5th. And by the way, the 2 sig figs in these ones just come from the subtraction or even from the 50 seconds. We're going to assume that we've got some sig figs on the 50 because the table says plus or minus 1 second. That gives us 2 sig figs. All right, so that's our NO2 and that's our NO. We get the same thing. So that is our rate from our initial rate. From 0 to 50 seconds, our rate is 2.1 times 10 to the minus 5th molar per second. How about for the period from 300 seconds to 350 seconds? What is that going to be? Let's go ahead and do it for O2 just because we haven't done O2 yet. Excuse me. The rate is going to be 1 over 1 times the change in the concentration of O2 over a change in time. If we go back up to that table, we figure out that our ending concentration of O2 was 0.0011. Our starting concentration was 0. And our time here is going to be 350 minus 300 seconds. And it looks something like that. And so what you end up with is 0.0011 molar divided by 50 seconds. And you get a number of 4 times 10 to the minus 6 molar per second. Wow, that's a really awful 10 to the minus 6. Let me fix that. 4 times 10 to the minus 6 molar per second, which is smaller than our other rate. Our other rate was 2.1 times 10 to the minus 5th molar per second. Later on, right, that was our initial rate. Later on, as things disappear, as we have less of the reactants available, our concentrations go down. We have 4 times 10 to the minus 6 molar per second as our rate. And so we're saying, hey, this kind of makes sense. It's consistent with what we thought. As time progresses, our concentration goes down. So that's how we might calculate concentration or a rate over different time intervals. Initial always means kind of the very beginning. There's a little bit of judgment about what data to use. And then very specific time intervals, you're just going to kind of find an average over that time. And we don't have any other data to work with, so that's what we have. All right, so here's another reaction. We've got A plus 2B going to C. And here we only have the data for B. We only have the concentration of B versus time. And I want to know what's the rate in the interval from 0 to 10 seconds. So this is your chance to try those calculations out and see what you come up with. All right, what'd you come up with? Well, hopefully you started writing down your basic definitions. Always start with basic definitions because they guide you. We know that the rate is defined for B as minus 1 over 2 times the change in the concentration of B over the change in time. And so we're going to go ahead and do that from the interval 0 to 10 seconds. So that's going to be minus 1 over 2. Concentration of B is 1.73 minus 2.00 molar over 10 minus 0 seconds. And that is our rate in the interval from 0 to 10 seconds. So 1.73 minus 2.00, we get negative 1/2 times negative 0.27 molar over 10 seconds. You plug that into a calculator, and you should get a positive 0.014 molar per second. Okay? 2 sig figs from that subtraction, even though we started off with 3 sig figs in our molarities, and we get a positive number. Why? Because rates are always positive. If you get a negative rate, you probably just forgot a negative somewhere, but you should check your work if you get a negative rate. So we got 0.014 molar per second. All right. There was supposed to be another problem in here. I'm not sure what happened to it, but this will suffice for now. So we have calculating rate using those definitions of rate. What we're going to keep doing is we're going to find there's different ways to define the rate. This is great when we have data versus time, but sometimes we don't have that. We have other information available to us, and so we're going to see different ways of calculating the rate. It's going to be the same rate. We should get the same number no matter which way we calculate it, but we're going to find there's alternate ways to calculate it as we go forward. Thanks for listening.